Okay, everyone, we have reached the point where we can now define what a function is, and then later we'll be interested in doing operation with functions. So first, let's define a function. Now, there are different ways we can define a function. There's like half a dozen different ways we can do this. I'm going to start by defining a function as a relation. Okay, so in other words, we're going to look at the relation definition of a function. So first of all, we need to define what a relation is. We're talking about a mathematical relation. Okay, and simply put, a relation is a set of ordered pairs. Remember, ordered means order is important, whether what number appears first, which one appears second. So we have a set of ordered pairs. Now, simple relation, 1, 2, there you go. Again, this is almost trivial, right? As long as I have one order set, that's the minimum number to have. So this is an example of a relation. Now, another relation would be, for instance, I have -2, 7, and 0, 5. Here's another relation. Okay, now let me make this a relation. And in this relation, I'm just randomly picking these numbers, by the way, nothing in particular. I'm not thinking of any formulas, anything fancy. So let's say I have these numbers. Okay, now this is clearly everything that we write in a set, as long as you have one order pair. So you do have a relation. This is a relation, no different than the others. Now, if you look at something interesting about this relation is that the first numbers are different. However, the second numbers, there is a repetition on the second number, right? So this is what I mean. If you look at these numbers, the first components of each ordered pair, each of those are different. Okay. Now, if I look at the second numbers, they are different, except a couple of them are the same. Okay. So this is indeed the definition of a function, and we use the letter F to indicate the set that is a function. Okay, so there we have it. So we're looking at the functional now relationship between the elements in the first elements in the set and the second elements in the set. So remember the requirement for the function. In order to have a function, the first components must be different in the relation. First components must be different. Okay, so let's agree on that one. Now, is it possible for the second components to be different, or do they have to be the same? Well, there's really no restriction on the second components for the function. However, we would like the second components to be different also, but that's for the different reason that we will talk about later. Okay, so here's again the relation definition of a function. Now, the other possible way I can do this is I can actually do the mapping definition of a function. So with the mapping definition, I'm writing the same components in the set above. So here I have the first set represents all the first numbers. The second set, I'm going to go 0, 4, 7. Notice, although I have two 4s, but we only write them once, not twice. Now, if I actually draw an arrow coming out of the first oval that you see, call these the x values, and the second numbers, we're going to call those for now the y values. So if I draw arrows coming out of set of x to set of y, then -1 would correspond to 0, right? And 2 corresponds to 4, as well as 3 corresponding to 4. And then 5, of course, corresponds to 7. So this is what we call the mapping from one set onto another set. Okay, now these lines that are drawn, each of these lines, courtesy of F. F is what makes these possible. Okay, the functional relationship between the sets are represented this way. Now, usually we don't write, F, 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 F like that. You can just put F on one of them, and that gets the message across. Okay, so the set of first numbers, these are the x values. The second numbers, we're going to agree, we're going to call those the y values. And the ordered pair has to be in that form, x comma y, not y comma x. X, we're going to call it independent variable, and y would be our dependent variable. Okay, so there we were just defining some terminologies. Now if I do another set, for example, let's say if this is a relation, another example. Suppose I have elements 3, 7, and let's go 2, 1, 2, -1. We're going to keep that simple. So again, if I look at the first components, let's see, oops, these are not different. These two are the same, right? So let me just say it suffices that two of them are the same. So this is not a function. Not a function. Okay. Now this not being a function, we'll look at this in a graph in a few minutes and see how this works out on the graph, as it was a graph of an equation that is versus one that is not a function. So we looked at, again, the relation, the mapping definition. Now, another way to look at this is in terms of a function machine. So with our function machine here, suppose I have something that looks like this. This is called a machine. This machine processes numbers. Okay, so for example, let's say the one that I have just directly above. A 3 goes in and it gets processed through this, and out comes a 7. So that's what a machine is. Now to be a function machine, I have to have a function. So let me make up a function f that works on this machine. Suppose I have 3, 7 and 2, -5. There you go. So however, whatever f is that causes this to happen, for 3 to map onto a 7, that's what f is. Now, typically, as we'll work with this later on, for us, these f's are going to be mathematical equations. Okay, so we're going to have mathematical expressions that represent the function. But for now, because I'm just making them up, so you don't see a formula or a function, an expression for the function. All right, so there you go. Another possibility, let's say the input is 2 and the out comes a -7. So in terms of a machine, then, as I just mentioned it, you heard me saying it, we think about in terms of input and output into and out of the machine. Okay, the inputs go into and the outputs come out of the machine. So that would be the output. So the first components are always the input. The second components are the output. All right, that would be in terms of a function machine. Now, every function has a domain and range. So let's agree the set of the x component, the x's are domain of the function, and the y's are a range of the function. So let's agree on that. So for instance, the example I have above, my domain is going to be made up of 3 and 2. You can put them from low to high, high to low. The order of elements in the set doesn't matter. Usually we go from low to high, but we can go any way you like it. The range would be the set of second numbers. I'm going to go in order for this one, -5, 7. And there we have it. We have the domain and range of that function. It's really that simple. Okay, so again, range is the set of all second numbers, the output. The range, we talk about the output values, and for domain, we talk about the input values. Now, domain is a very important concept because in order to what we call evaluate functions, we need to know what we can put in, what the inputs could be into a function. So for example, suppose my function machine now f is square root of x. Okay, and then, so for this one, let's say I put a 2 input, output would be what? Square root of 2, whatever that is. No need a calculator. You put in a 25, output would be 5. Now into this machine, into our function machine, what if I put in a -4? and the function is going to try to process this. So what's going to come out at the end? The other side. Remember, so that's going to be, the machine is trying to process square root of -4, but square root of -4, if this is a machine that processes only real valued functions, then because square root of -4 is imaginary, right? Not real. So there will be no output as a result of this, right? So you will see nothing coming out of the other side of that machine. So that's why domain is important. And the reason is because the domain of a square root, the radicand has to be at least 0. So there you go. In order to see an output, you should put anything 0 or higher so you can see an output. That's why domain is very important in our work. Okay, let's take a look at another example. Suppose this time I'm going to give you a t-chart. Again, numbers, I'm just making these numbers up, entirely optional. 4, 0, and 2, -3. How's that? So we want to list the elements of the domain. So domain, all first numbers, the x numbers, right? So it's going to be -2, 3, 5, 7. And what would the range be? The range, of course, the set of second numbers. That would be, let me put them in order just so they look aesthetically nice, I guess, in the eyes of the beholder, right? There you go. To us, that's like, wow, that's nice. Because it goes from low to high. And there you have it. Now, what if I have the graph of a function? Can I determine the range and the domain of the function? Of course. So I'm going to make something up here, very rough and crude. And for this one, let's say here's my x-axis. I'm going to throw in the y-axis on there. And this point, the low point, I'm going to call it -1. And there you have it. Now, remember, on the graph of this function would be, or this graph, the arrows on the graph means they extend indefinitely in that same pattern in the direction of the arrow. Okay, so we want to find the domain and the range. Okay, now in order to look at domain, remember domain is all possible x values. So for domain, we look at the x-axis. And looks like regardless of what I pick for x, there's always going to be a corresponding y, true, on this graph. So again, remember the arrow means this goes forever. So you can go to the right and however as far as you like, and there will be a value of y, an output as a result. Therefore, the domain of this function is going to be -infinity to infinity. So keep in mind, domain means values along the x-axis. So these are domain values. Now for range, we're going to look at the y-axis. Okay, so for range now, if you look, there is no point below -1, right? There's nothing here. There are no values below -1 along the y-axis. So for range, we're looking at the y-axis, but looks like as if as I go higher and higher in both direction, there's always going to be a y, right, along the y-axis. So for that reason, we're going to say the range of this function, is going to be from the minimum, from the low point of -1, including -1, and it extends to infinity all the way up. All right. And there you have it. So remember, for range, we look at the y-axis. For domain, we look at the x-axis. And if you think about in terms of infinities at both ends of both number lines here, the x and the y-axes, so that will help you kind of look at the interval notation that I have here, why the infinities appear the way they do. All right, so there you have it. That would be determining the domain and range from the graph. Let's try another example of this one. Okay, so for this example, again, I'm just going to draw an oval here, and here's the x, there is the y. And I'm just again making up these numbers. I have a 5 here. Let's go -5 here. Let's go 2 here, and or it doesn't matter. Let's go this one, and then I have this upper portion. I'm trying to draw an ellipse in case you wondered. There you go. It looks like an ellipse, doesn't it? Alright, so this one up above, let's say that's 2, and this point's now -2. Okay, so let's do our domain and range of this one. Remember, domain is all possible x values, and the range would be all possible y values. Now, if I look at the possible x values, I only have x values for which this equation is defined between -5 and 5, right? Because I don't have a graph here. I don't have any portion of the graph here. So x cannot be outside of -5 and 5. So we're going to say the domain of this function is from -5 to 5. Now, if I look at the range values, remember for range we look at the y-axis. So there you go. These are the y values. And how are those values? So look at this one. See? There you go. That's a value of y. Here's a value of y for that point, for this point. This one, there you go, a y value there. So it's for that reason we're looking at those y values. Okay, and then let's see. So the range is going to be between -2 and 2. Perfect. There you go. So this function is range bound between -2 and 2, and it is domain bound between -5 and 5. Let's take a look at, let's try a different idea. I think we've done enough domain and ranges. Now let's take a look at a function, a relation that is not a function for this next idea. A relation that is not a function. So I'm just going to make something like this one, 3, 2, 3, -2. Okay, now if I plot these 2 points on the Cartesian coordinate system, let's say here's 3, 2, and this point there is 3, and this would be 3, -2. So I plotted a couple of points here, right? Now, because the first numbers are the same, we know that this is not a function, right? So this is not a function as we stated it. Now, something interesting happens here on the graph of when we plotted these 2 points. If I draw a vertical line through these points, the line will go through both points because the line will go at 3, right? It will go through x equals 3. Remember, the coordinates of this point are 3, 2, and the coordinates of the point below it are 3, -2. So a vertical line drawn through these will go through both points, and you can see now the first components are the same, right? So we can actually do this, and it actually is called what we've just done. There is a vertical line test. So the vertical line test is a test to determine whether the equation, the relation, is a function or not. Okay, and the way this vertical line test works is you can draw a vertical line anywhere along the graph of the equation that's displayed, and if it crosses at 2 or more, then the graph does not represent a function. So let's say here I have some graph, and if I draw a vertical line, well, now let me do this because the y-axis was my vertical line. I want to just do something that's not there. This is again a relation, but this is not going to be a functional relationship between x and y, because I can draw the vertical line and you can see that the line drawn crosses the graph at not 2 but 3 points. Okay, so that's how the vertical line test works. 2 or more. Therefore, this graph does not represent a functional relationship between x and y. So the graph is not a function. I use FNC short for function. A lot of people do that. Okay, so there you have it, the vertical line test we talked about. Now let's see how we can define again or determine the domain when we don't have a relation but we have an equation, because later on that's how we're going to be given these functions in the form of a mathematical expression. Now, a lot of times, if you can graph them, for most of what we do, they're graphable at our capacity. We will be able to graph them. So graphs are a great guide as to what the domain and ranges are. But for this one, without graphing it, when we graph these in the section on graphing linear equations, which we'll do more of that later on also when we look at linear functions. But for this one, if you graph it, the graph's going to be a line, right? A straight line. But for now, you can see just by arguing that x can be anything true. There's no restriction for x. Can be 0, positive, negative, right? So, and we'll be able to evaluate 4 plus that. The key is, can I do the arithmetic once I plug in for x? Can I do the arithmetic of that expression? If I can and get an output, then that number is in the domain. So for this one, domain is going to be negative infinity to infinity, means x can be anything. So this is the interval notation, or we can go in set builder notation. X is a real number. Or I can simply use the funny looking R, that means real numbers. So all three ways are acceptable here. Now what about the range? Well, if you look at the range again, y could be 0 when x is negative 4. Y for x positive, greater than 4, like 5, 6, and so on. Y would be positive all the way to infinity. And for negative x values below, let's say, negative 4, like negative 5, negative 6, negative 7, and so forth, y would take on an infinite number of negative values. So again, there is no restriction on the outputs. The outputs could go from negative infinity to infinity. All right, so that's how you determine that one. Now let's take a look at another example. Find the domain and range of, let's say we want to find it for this one. I have 7 over x plus 2. Now with fractions, we usually look at what makes the denominator 0. Remember, in a fraction, division by 0 is undefined. The numerator could be 0, but not the denominator. All right, so this one, looking at this, x cannot be negative 2, right? Because you get division by 0. Negative 2 plus 2 is 0. Therefore, we're going to exclude a negative 2, but any other value of x is possible, right? So we can write this in interval notation. Anything from negative infinity up to negative 2, but not including. So this is how we exclude a point on the number line using interval notation. So if you look at, for example, this is negative 2. We were coming negative infinity up to negative 2. Okay, and then we pick it up just to the right of that from negative 2 to infinity. That covers this segment. This covers that segment of this real number 9. Okay, and there's our number line. The interval notation. So that's the domain. Domain, it could be any of those. Now what about the range? Now if you look at the range again, when x is positive, fraction is positive. I mean, for x greater than 2, really, let's see. X plus 2 less than 0, x. Okay. For x less than negative 2, this fraction is negative. For x greater than negative 2, the fraction is positive. Here, the fraction is negative. But the key is that the y values could be positive or negative, right? And can they be 0? Can the y be 0? Well, the only way a fraction can be 0 is if the numerator is 0, correct? Here we go. I make a fraction over x plus 9. How can this fraction be 0? Because the denominator cannot be, the numerator has to be. The only way this is equal to 0 is if the question mark is 0. All right. Now look at the fraction I have here in my example. The numerator of that fraction is 7. Okay, so I'm just going to say, since numerator is not 0, therefore y cannot be 0. And there is the exclusion in the domain. Remember, domain, set of all y values. So, I'm sorry, the range, the set of all values, y values. Domain is a set of all x values. Therefore, my range in here is going to be anything. Negative is fine. Remember, the fraction could be negative. So it's negative infinity up to 0, not including 0, union. 0 to infinity, because the fraction could be positive. And this would be our range, the answer to range. All right, so glad we worked this one out. Let's take a look at another example. Suppose this time I'm making a square root expression, 3x plus 6. And we want to determine the range and domain of this one. Now, because we have a radical here, for all our square roots, we work with square roots quite often. So for square roots, the radicand, what's under the radical sign, has to be at least 0, right? Cannot be negative, because otherwise the function is not a real function. It will be a complex function. And again, in this course, we're just interested in real functions. So I'm going to set the radicand 3x plus 6 greater than or equal to 0. Subtract 6 and divide by 3. And there you go. So this would be the domain of this expression. The radicand must be at least negative 2. So that means negative 2 to infinity. That is the domain. Or we can say all x such that x is greater than or equal to negative 2. That will give us our set builder notation. And that's our domain. What about the range? The range, well, for a given domain, the square root is always positive, correct? Remember the symbol, the mere symbol, this means principal root, right? And principal means positive root. So the range is going to be from 0 to infinity. 0 is when x is negative 2. That will be square root of 0, which is 0. That's the beginning of the values of y. All right, and there we have it. Now we're going to finish with function notation. You probably have seen it, but it's just a reminder. Let's talk about a notation here. When we say notation, that means a way of writing or showing something. The common convention. So the common convention or the notation for function is f of x. So we often write y equal f of x, and we read this y is a function of x, right? So we can say f of x. I'm reading what's on the right side. That's read as f of x, and some people call it f at x. So there's some flexibility there. So anything outside of that, just got to be careful. Make sure that it reads properly. One thing that it's not f times x. Okay, so be careful. F times x. That's not true, because f times x like that, right? We don't mean it in that way at all. At all. This isn't what we're meaning. It's just a notation. So there you have it. Now in this notation, y or f of x again is a dependent variable, and x is what we call the independent variable. The idea is that you plug in an x, the choice of x is independent of f of x. You choose a value of x and you see that's your input. Remember, in the machine, the inputs are up to us what we put in. So those are independent. But once you put in an input, then the output pretty much is dependent on what went into the machine, on the input values. So it's for that reason they're called independent dependent variables. All right. Now, to give you an example, let's say I have f of x is equal to x cubed minus 5. And I want to evaluate this function. When we plug into the function, it's called evaluating the function. I want to evaluate this function when x is 2. In other words, when the input, let's look at our machine here. Here's the machine f. The instruction to the machine is to cube the input, subtract 5 from it. So in this machine, I'm going to put in a 2. I want to know what's going to come out from the other side of the machine. So you put the 2, the machine will cube it, takes away 5 from it. That will be 8 minus 5, or 3. So in this case, the output is 3. So we're going to say f evaluated at 2 is 3, and that's the function notation for this process. So f at 2 is 3. Therefore, the ordered pair 2, 3 would be a point on the graph of this function. Later on, we'll look at those. Now, we often work with numbers, but sometimes we work with variable expressions. So what is f at m? This time I'm putting in an m. Remember, the machine takes whatever they input, cubes it, subtracts 5. So there is your output. Now, because I don't have a number, I have a letter. The output also has a letter in it, right? What if I put in, let's say, put an apple into this? I know you cannot process apples through this function machine, but it's just more symbolic than anything. All right, so what if I drop in an apple? What happens to that apple? Well, the machine will take that apple, right? It will take it, and then it will cube it, subtracts 5 from it. It doesn't care what you drop in, right? Anything that goes in gets cubed, and then 5 taken away from it. What if I drop in the square root of x into this? Well, anything that goes in, a square root of x goes in, gets cubed, subtract 5 there, without simplifying it, but that's what happens. Okay, so that's called evaluating the function at specific points. Okay, now almost done with this work. Let's take a look at some examples, general examples now. Actually, let me hold that thought. There's one other thing I might as well talk about in here now, and then truly we'll be done with the lecture portion. Then I can look at all the examples that follow. So let's talk about increasing, decreasing, and constant functions. Okay, so those are the 3 types of functions. Now, in order for this to work, the assumption is that we have a function that is defined on an open interval. So let me just put our assumption. Assume a function, call it f. F is defined on an open interval. Okay, and that interval, we're going to call it open interval I for an interval. Okay. Now, let's take a look at the case where we have an increasing function. And I'm just going to draw some rough sketch here. So for this one, I'm going to actually take a look at an increasing function. Let's take a look at the increasing function. So here I have a function. Let's call this point A, and this point is B. So the y value would be f at A, and the b values, y would be f at B. Remember, A and B are on the x-axis. Y equals f of A, and the other one, f at B. These are along the y-axis. Now, clearly, you can see this function is increasing because the value of the function at B is higher or greater than the value of the function at A. So this function is what we call increasing function. So in order to be increasing, a function to be increasing, that means if a is less than b, because remember b is to the right of a, as you go from left to right. If a is less than b, then f at a will be less than f at b. Okay, that would be the sign of a function that is, we're going to call the increasing function. Example of decreasing function, you can kind of imagine what that one would look like. Let's say I have something like this now. Suppose this is a and this is b. So here I have f at a. The higher point now is f at a, the lower point is f at b. So for this one, the function f is decreasing. So that means f at a is higher, greater than f at b. Okay. Whenever a is less than b. So you go from higher point to the lower point, and that would be the sign of a decreasing function. And finally, we're going to take a look at the function that is constant. So we're going to look at a constant function like this one. Function that's flatlining. So this is what f of x is. All right, now for this one, I have two different points, a and b. Of course, a is less than b, but it could be any 2 points, doesn't matter, as long as you have 2 points. Now, if you look at the value of the function, this would be f at a, the y value, f at b, the y value at b. Those are exactly the same values, right? They're the same distance away from the x-axis. So for function, therefore, to be a constant function, we're just going to say the constant function is given by f at a will equal to f at b, this time whenever a is different from b. As long as they're different, again, it doesn't matter which is greater, which is smaller. So there we have the 3 flavors of function behavior. A function could be increasing, decreasing, or constant. It can only be 3 of these. Now, the graph of a function could have 1 or more of these, right? We could have 1 or more of these on the graph of a function. So let me actually bring my nice coordinate system. There you go. And suppose I have something here. Okay, so I'm going to call this the x, and this is going to be my y. All right, and I'm just purely making up these numbers and the graph. So suppose my graph looks like this. Oh, this part of it isn't, I meant for this part to be flat like that. Oops, this whole thing is going to go away. Yes, don't worry, we'll redraw it. So I wanted to go like this, curve, come back up, go flat, and then go down. There you go. Looks like the stock market, huh? So it's going to rise, and then it's going to wobble a little bit, flat line. It's going to flat line here, and then it's just going to nosedive. Alrighty, so my points now. Let's say I'm interested in over the entire domain. Okay, it means entire number line. Now the key points here, let's say that peak is at A. The trough, we're going to make it at B. And here, the point where they transition from one to another form. Transition from one to another. So I have A, B, C, D. Okay, you can go also X1, X2, like that, X3, X4. Okay. In fact, let me do, because I think in most textbooks they do that. Again, depending on the textbook, it's really not a big deal. Just a notation, right? So there we have it. Now we want to determine the intervals over which the function is increasing, decreasing, or it is flatlining, that is constant. Now remember, because our function is defined on an open interval, I defined it up, did I write it? Yes, open interval. Okay, so because of that, we are not interested what happens at a point. Okay, so this is what I mean. Let's put increasing, and then we're going to put decreasing below it, and we're going to go constant. They don't have to be in that order, by the way. Just need 3 categories, and that's how I chose them. So let's go increasing. As we go from left to right, on the number line, okay, that's what determines. So I'm going in this direction on the number line, okay. Now let's take a look at the function value. The function is going higher up to this point. So it looks like from, as far as x goes, remember, we're coming from negative infinity going to infinity. We're going in this direction. The increasing, decreasing constant reference to the x values, okay, not the function values. So the function is increasing over the open interval from negative infinity up to x1, right? Again, right in here, it's increasing. And then from x1 to x2, notice it dips down. It goes down. And so it's decreasing from an open interval from x1 to x2. Now, here's what I meant. We're not interested in the increasing, decreasing at a point. So for this one, the point would be x1. It's like, what is the function doing at that point? Where that is kind of a transition point, isn't it? From high to low. So the point itself, we don't count it. We don't use bracket. And let me just mention that some of the textbooks actually do use brackets. So technically speaking, because the way we define it, we shouldn't have the bracket, but there's really not a consensus, unfortunately, among mathematicians on this one. So some use closed intervals. I guess those are the ones, the proponents of maintaining continuity, because see, if you have open parentheses at x1 in both directions, and what about at x1? It seems like the function isn't defined. But to me, that's not the justification. Okay, so we went from x1 to x2. Let's see, now I'm going from x2 to x3. We're going to go in that direction. The function clearly is increasing, so I'm going to go union, means or. So it's increasing from there to there, and from x2 to x3, it's increasing. All right. Now it's flatlining from x3 to x4. So it's going to be constant from x3 to x4. And after that, that's when it's beginning to descend, to drop. So it's going to be decreasing from there until the end. That would be from x4 to infinity. Going forward, it's just going to decrease. And there you have it. That's how you determine that based on the graph of a function. All right. Now we can take a look at some. Let's take a look at some examples. Okay, so in this first example, let's say we want to know if this relation defines a function. We've done several of those, but let me do this one also. Suppose my relation is 2, 4, 0, 2, and 2, 6. Okay, we want to know if that relation defines a function. Now remember, we look at the first component, and the first numbers must be different. Aha, look at those two. These are the same. So that's going to rule out a function. This is not a function. See, it's that simple. What about the graph of a function? Let me just make another one up. Suppose I have a graph of an equation or a relation looks like that. Can that graph represent a function? Okay, what do you think? Remember, for the graph, we do a vertical line test. It looks like it's crossing it at only one point, so this graph does represent a functional relationship between x and y. So that is a function. Okay, got that one. Let's take a look at, again, whether the relation defines y as a function of x. This time I'm going to make like an algebraic expression like we would expect it to be, y equal x squared. Again, this one, because for each x, you get a different, we'll never have the same x, right? We'll have always different values of x. So x's will always be different in this one. Therefore, domain is all real numbers. This is a functional relationship because we never have a situation where the same x will define two different y values. So x can be anything, 0, negative, positive, doesn't matter. Now, because x squared is always positive, right? X squared is always positive. It's never negative. 0 is the lowest it can be. So for that reason, the range is going to be 0, which happens at x0, and it's never negative, so it's always going to be positive. Therefore, it's going to be from 0 to infinity. All right, we got that one down. Let's take a look at another one. How about if I do x equal y to the 6 now? This time, note, y to the 6 is always positive, right? This is always positive. So that would imply that the domain of this function is always positive, which is x, because y to the 6, 0 is the lowest when y is 0. So my domain, therefore, is going to be from 0 to infinity. And what about the range? Again, y could be anything, right? I can always give me any number. We can write it to the 6th power. So y is from negative to infinity to infinity. Now the question is this a function? Well, if I can find for same x two different y values, then it's not a function, right? So let's check out. Let y be 2. Okay. Well, 2 to the 6, which is x, is going to be, what, 2 to the 6 is 64, right? What about when y is negative 2? Y negative 2, negative 2 to the 6 is also 64, right? So note in here I have 64 comma negative 2, and for the previous one I have 64 comma 2. And you can see that I have same x, two different y values, and that defies the definition of a function. These are the same. So it is possible to get two different y values for the same x. Therefore, this one is not a function. Now, if a relation is not a function, it's not like it's the end of the world. All that means is that the things we can do that require we have a function, we just cannot do it with expression like x equal y to the 6. That's all that means. It's just we don't have the privilege of working with these functions, with these relations like we do with functions. Alrighty, let's take a look at another example. This example, how about y equal, let's say, square root of 4x plus 1? How's this going to work out? Well, for this one again, x can be, as long as the domain, remember, we call this implied domain, by the way, because in general, that's implied. We know the radicand has to be positive. That's implied, quote unquote. So we often talk about implied domain of radicals, especially square roots. Implied domain says radicand must be at least 0. So if I do that, subtract 1 from both sides, divide both sides by 4, then I have x greater than or equal to negative 1/4. And that is indeed the domain, x such that x is greater than or equal negative 1/4. Now, in interval notation, that means everything above -1/4, right? So on the number line, that's what it's going to look like. The interval notation is going to be -1/4 to infinity. So this is, again, the domain. Now, what about the range? Again, the range, the fact that we have the radical sign, this means principal root. And it has to be positive by definition. Otherwise, we wouldn't use that symbol. Well, we just said positive, so y would be greater than or equal to 0. At -1/4, it assumes its lowest value, and thereafter it gets higher and larger values. Therefore, our range is going to be from 0 to infinity. All right, now, question, is this a function? So we have the domain and range of the relation. Now let's see if this is a function. Remember, to be a function, we are not allowed to have same x with two different y values, and you can see by inspection that there is impossible for same x to get two different y values. The only way I can get two different y values if this was plus minus in front. You see that? And it's not, it's just positive. So square root of 4x plus 1 is a function. Perfect. So there we have that one as well. Now let's do one where we want to, let's say we want to evaluate the function. All right, so I'm just going to make up this one. Let's say my f of x is going to be -3x plus 4. And I'm going to let x be 1/3. So we're going to plug in f at 1/3 is -3 times 1/3 plus 4. -1/3 of 1 is -1 plus 4 is positive 3. And there you have it. What if we want to do, I don't know, let's do another one. F, we'll call this g of x. This one I'm going to make it -x squared plus 4x plus 1. And this time we want to do g at 1/2. Okay, so g at 1/2, we put 1/2 in parentheses squared plus 4 times 1/2 plus 1. I always have a habit of putting x's in parentheses in an expression if there is a number before x or a sign other than a positive sign. So it just leads to the correct computation or evaluation. Notice the first term is -1/2 squared. So order of operation requires I do parentheses. So I have to, and then exponents. Well, parentheses is inside parentheses. I have 1/2. I just have to square it. 1/2 squared is 1/4. Notice the negative stays. You don't square the negative. You would square it only if it was -1/2 squared like that. Then in that case, it would have been 1/4. But this is negative on the outside of the parentheses. All right, and plus 4 times 1/2 is 2. 2 plus 1 is 3. 3 take away 1/4 is 2 3/4. So there you go. That's g at 1/2. You're welcome to write it as a mixed number, or you can write it as an improper fraction. You multiply 4 times 2, 8. Add 3, the numerator, to it, divided by 4, and we get 11/4 for the number. And there you have it. Again, the bottom one, the last number, 11/4 is what we call an improper fraction. 2 3/4 is what we call the mixed number. And there you have that one. Let's take a look at maybe, how about, I don't know, one more. It's always good to do one more. And we will be able to finish this video under 1 hour. That's good. So this one, let's say we have an equation that has both x and y together. This is like a linear equation in 2 variables, right? So let's say we want to rewrite this using function notation. So I'm going to rewrite using f of x. So to do that, because remember, y and f of x for us in case of functions, y and f of x are the same thing. So all I have to do is solve the equation for y. I'm going to subtract x from both sides and divide both sides by 3. And that's what we get. At this point, we just replace y with f of x, so that the f of x is going to be 4 negative 1/3 x. Now if you write it as negative 1/3 x plus 4 like this, that's also fine. If you go negative x over 3 plus 4, that's also fine as well. So I'm just writing it, the most common way of writing it in textbooks. And there you have it, right, using f of x. Okay, now once we've done this, suppose I want to find f at 3. Once we have the notation, we just plug in 3 for x. Remember, the numbers in parentheses, these are the x values. And that would be 4 minus 1/3 times 3. And 1/3 of 3, that's 1. But it was minus 1, and 4 minus 1 is 3. And there you have it. So the answer is 3. Just so happen the input output are the same for this selected value. And there you have it. So hopefully this video helped you a refresher on functions, because oftentimes a student forget what is the definition of a function. So I think we did a thorough job at trying to explain this concept of functions. All right, so with that, we are done with this particular video. Again, as always, thank you for watching the video.